Hello everyone. In this video I'm just going to go over the last little bit of stuff we talked about with the can crush activity and also start going over a little bit of the notes on gases and how they behave. Now at the top of this paper, and you might notice I have a yellow paper here. Your paper might be a different color because I changed the colors from each class period. But what I want to talk a little bit about at the top here, and I kind of covered up this box on purpose, I want you to write down what questions you still have left about the can crush. There's no wrong answers to this, so make sure that if you haven't watched my can crush video or you didn't see it in class, that you watch that video and then write down a couple questions that you have about the can crush. No wrong answers to the question part up here that I'm not showing you, but I do want you to write down a couple questions you still have. Now, I'm going to talk a little bit about what most of the classes think is going on. So maybe you missed the discussion day. So let's have a little conversation about what might be going on in that can crush. So what most of my classes agreed on is that water vapor in the can was very, very hot, and then it cooled down. And when gases cool down, they condense. So we all kind of agreed that the water vapor in that can is condensing. So the density of it changes and the shape and the temperature of it change as well. Now what started getting us a little confused, where people were getting a little stuck, was why is it that the gas, when the vapor condenses, why does the can get crushed in with it? Now we did not answer this question yet. We're going to answer at the end of our unit. But some people thought maybe the can was being pulled in by that gas. Maybe there's some kind of change in pressure happening here. But what we're not sure about is why is the can crushing? Why is it crushing? So we know the water vapor condenses. We know that it gets closer together when it does that. But what we're still stuck on is, how is that can crushing so quickly? And how does pressure affect it? So I don't have an answer for you yet, but write this down in your paper and get a little idea of what the classes were thinking about when we were talking about this. Now, for our Bellwork that day, we brainstormed what gases look like, and we came up with a class answer. So we said that the particles are spread out, they're all over the place. They're moving very fast. And those particles can bounce off of each other, and they can bounce off of surfaces. So the way we represented this, we drew particles as circles. We're not worrying about which particles are which or which circles are what. We're just going to draw a circle to represent those gas particles. We also are representing speed using these little lines. It's kind of like if you draw someone running. Here's my running person. You draw the little lines behind them to show they're running, and it also shows us what direction they're moving. So we have all these gas particles, they're flying around, they're moving very fast, they're bumping into walls, they're bumping into each other, and they're not thinking about anything, they're just bumbling around, moving really fast, flying all over the place. Okay? So we're going to use this kind of as our basic idea of what do gas particles look like. Now we have a couple terms we need to talk about. Our first term is pressure. Pressure is the force applied to the surface of an area. So I can press down on this table. I am applying a force. I am applying pressure to the table. Now, temperature is the measure of the kinetic energy. Kinetic energy is the energy of motion. So really, temperature is just averaging out all the speed of our particles and telling us how fast our particles are moving. So if it gets colder, they're moving slower, and if it gets hotter, they're moving faster. We also have volume, and we should know by now volume is the amount of space something takes up. Now we're going to use these little shorthands throughout the unit. If something is changing, we put a delta symbol, which just looks like a triangle. So for example, delta T would be change in temperature. If something increases, we're going to use a little up arrow, and if something decreases, we're going to use a little down arrow. Now I added something at the bottom, so make sure you add this. We have 4 abbreviations we're going to use. Pressure is P, temperature is T, volume is V, and amount of particles is N. Okay, so counting those particles is N. Now we have units we're going to use for each of these. The first unit is called atmospheres. Atmospheres is abbreviated as ATMs, and it measures pressure. So around us at every given time, all the time, there is air pressure. And air pressure can change depending on where you are, how high up in the air you are. So the pressure we talk about here, we measure in ATMs called atmospheres because the atmosphere pushes pressure on our body. The standard pressure around us at any given time is about 1 atmosphere. So we have 1 atmosphere of pressure pushing down on our bodies at every given minute. Now our next unit is called Kelvin. It's for temperature. Now we're not using Celsius or Fahrenheit here for temperature. We're using Kelvin because Kelvin is always positive. So the coldest temperature possible is 0 Kelvin. Now we have not actually gotten temperatures that cold. We have gotten them very, very close. But what we theorize would happen at 0 Kelvin, or absolute 0, is that particles would actually stop moving. So we set up here, temperature is just a measure of the particle's speed. So if we get it to that coldest temperature possible, 0 Kelvin, we theorize that their speed goes all the way down to 0 and those atoms stop moving. We don't know that for sure yet though, because we haven't actually gotten it to absolute 0, but we've gotten very close and those particles slow down and down and down and down. Now the reason we use Kelvin is because it's always positive, and when we plug stuff into equations, negative numbers mess up our calculations. So scientists use Kelvin because it's always positive, and that way our calculations never get messed up. Volume, we're going to measure in milliliters or liters, depending on how big our sample is. So if it's smaller, we'll use milliliters. If it's bigger, we'll use liters. And then our last one, the amount of particles, is measured in what's called a mole. Now, a mole is a new unit for us, and it sounds a little silly, and it's abbreviated as MOL. Now, a mole is 6.02 times 10 to the 23rd particles. It's kind of like if you have a dozen. A dozen, 1 dozen, is always going to equal 12 of something. So if I have a dozen eggs, it's 12 eggs. If I have a dozen roses, it's 12 roses. If I have a dozen cookies, it's 12 cookies. No matter what, it's going to be 12 when I say 1 dozen. And the reason we use this dozen is so bakers don't have to say I have 36 eggs. They can say I need 3 dozen eggs. The same idea is true for the mole. For the mole, 1 mole is equal to 6 with 23 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That many particles. So when I'm measuring the amount of particles I have, we measure in moles because chemists don't want to talk about big numbers like this. They don't want to have to say I have 6.02 times 10 to the 23rd. They don't want to have to say 6 with his 23 zeros after it. So instead, they say, you know what? Let's say that a group of atoms this big is 1 mole. Just like bakers say, a group of 12 eggs is 1 dozen. Now, I'm going to go grab something I forgot to grab real quick. I have a box, and I'm going to try and lift this up for a minute. Bloop. And floopy. Bloop. I have a box here. This box is 1 mole of gas. Okay? So 1 mole of gas takes up this much space. So in this box, I have 6.02 times 10 to the 23rd molecules or particles of gas. And that takes up this much space. Now, if I was talking about a mole of water, water particles are much closer together, so a mole of water is just a couple tablespoons, like a little bit in my hand. But a mole of gas takes up more space because those particles are more spread out. So when we're talking about gases and we talk about particles, 1 mole is about this much gas. Okay? Okay, so if you are missing anything from these notes, please make sure you get them down, especially this diagram at the bottom. And don't forget, at the top of this page, you had to do a little brainstorm. What questions do you still have about the can crush? Okay, I hope this helped, and have a beautiful, beautiful day.